Welcome to The Explainer. Today, we're taking something that can honestly feel like a pretty abstract engineering concept, electrical power flow on an offshore rig, and transforming it into a clear visual journey. If you've ever stared at a highly complex rig schematic and just felt overwhelmed by the sheer volume of lines and symbols, well, this is absolutely for you. We're going to strip away all that noise and trace the exact path of power, literally from generation all the way down to the heavy mechanical lifting.
To kick things off, I want you to think about a concept that's as simple as it is mind-blowing. Picture a rig floor at 2 in the morning. A driller nudges a joystick, and a massive drawworks springs into action, easily hoisting thousands of feet of heavy drill pipe. Well, every single watt of that massive torque at the drawworks originates from a single, traceable source: diesel fuel. And by the end of this explainer, you're going to be able to follow that exact energy path with your eyes closed.
All right, let's dive right into this. If you can commit these 5 steps to memory, you will never lose the thread of a power system drawing ever again. We're going to trace a single line moving straight from left to right. It goes generator, to switchboard, to transformer, to converter, and finally motor. This is the universal sequence, the absolute backbone of power application on modern drilling vessels. When you look at a real-world AC drilling control interface, you can actually see these exact stages at play. You've got your main incoming supplies up at the top, routing down through the transformers, into the diode bridges, right across that common DC bus, and finally out through the inverters to the specific motors, things like your drawworks, mud pumps, and top drive. It might look super complex at first glance, but it's really just our 5-step path applied at scale. So let's break those steps down. Step 1 is generation. This all starts deep down in the engine room with the diesel generator sets. And a rig doesn't rely on just one. Usually, you've got several gen sets running in parallel. That built-in redundancy is absolutely crucial because it ensures that if one unit trips, operations just keep running safely without a blackout. So each alternator is spinning, producing alternating current, or AC power, at medium voltage, which on larger rigs is commonly 6.6 kilovolts. Now, once that 6.6 kilovolt power is generated, it doesn't just wander aimlessly around the hull. It has a specific destination. You can essentially trace those massive cables from the glowing bus bars of the diesel generators straight into the rig's main electrical distribution hub, and that is the high-voltage switchboard. You can really think of the high-voltage switchboard as the rig's ultimate traffic cop. It basically sits there deciding exactly where this massive influx of medium-voltage power needs to be routed. It splits the power up by load type across the entire vessel. So a portion goes to your drilling loads, another massive chunk goes to propulsion and thrusters for dynamic positioning, and another branch heads off to the hotel loads, powering the accommodation blocks so the crew has lights, climate control, and of course, hot coffee. For drilling drive systems specifically, one or more feeders run right out from that switchboard. But I have a quick question for you to test your instincts. Variable speed drives and drilling motors definitely do not operate at 6.6 kilovolts directly. So somewhere in this chain, the voltage has to step down to a manageable drive-level voltage. But where exactly does that happen? Take a second and think about it. Well, if you guessed the transformer, you nailed it. It doesn't step down at the generator, and it doesn't step down inside the switchboard itself. That voltage step-down happens precisely at the transformer, which is positioned perfectly between the high-voltage switchboard and the converter panel. And there's actually a really fantastic engineering rule of thumb at play right here. Transformers take that primary winding of high voltage from the switchboard and step it down on the secondary winding to match whatever specific voltage the variable speed drive system needs on its input. Very often in these systems, that means knocking that 6.6 kilovolts all the way down to 690 volts. It's essentially an adapter that is perfectly sized for the drive. From the transformer, that 690 volt power enters stage 4, which is the converter panel. You can consider this the absolute brains of the system. We aren't just blindly passing power through anymore, we're meticulously conditioning it. The converter panel takes that fixed AC power, rectifies it into direct current, or DC, and then essentially rebuilds it, inverting it back out into variable frequency AC. And that brings us to the final leg of our single-line journey. That beautifully conditioned variable frequency AC power flows right out of the converter and hits the mechanical application. It drives the motor, which turns the shaft, which spins the drawworks drum, spooling the wire rope, and physically lifting the load on the rig floor. We have literally gone from a drop of diesel to physical, heavy lifting torque. But hold on, before we celebrate mastering this, we have to talk about how this can all go wrong. This is a critical failure mode that requires some real systems thinking. Imagine this electrical path as a physical chain. The golden rule here is you must size the whole path, not just the motor. Because the weakest link in this chain, that is exactly what dictates your total maximum performance. Let's look at the real-world consequences of this. You could literally spend a fortune buying the most incredible, top-of-the-line variable speed drive and an absolute beast of a drilling motor. But if you have an undersized transformer upstream, or even just a poorly rated feeder breaker sitting back in the switchboard, you've created a massive bottleneck. That single weak point will completely throttle your drawworks performance, and all that expensive downstream hardware is totally wasted. The whole path has to be sized together, period.
So, the big takeaway here is that power flow shouldn't be some abstract engineering phrase to you anymore. It's a permanently changeable concept. Let's do a quick recap of the 5 stages we've conquered. Diesel gensets generate the power. The high-voltage switchboard distributes it. Transformers step the voltage down. Converter panels condition it into variable frequency AC. And finally, drilling motors apply it, turning it into raw torque. You have just mastered the foundational knowledge of how these mechanical systems get their power.
Now, you've seen the converter panel from the outside as just one single step in the chain. But what's actually happening inside that box? Well, if you open any variable speed drive cabinet on any rig in the world, you're going to find the exact same 3 stages doing the exact same 3 jobs: rectify, store in the DC link, and invert. It's an incredibly efficient process and is exactly why AC drive technology has completely replaced DC systems on every single rig built in the last 3 decades. Which leaves us with this final thought. You now completely understand the entire macro path from diesel all the way to drawworks. But if you can crack open that converter panel and truly master how a VSD rectifies AC to DC, stores it in a DC link, and inverts it back to control motor speed with pinpoint accuracy, well, are you ready to decode every single modern drive schematic on the market? Because that is exactly what we'll be tackling next. Keep that curiosity alive, and thanks for exploring with us.